All right, thanks for having me. Yeah, sorry, I've got my headphones on so that we get better sound for the people online. Um, yeah, so as Mark introduced, I'm Wolfgang Mayer. I'm associate professor in the Industrial AI Research Center. And so my background's machine learning language processing. And so today my brief here is to give you an introduction of how AI works. Um, I'm not assuming you know a lot about AI, so maybe some of the talk will be a little bit basic for you. I just want to give you an overview about what the main uh, techniques are in AI and how the field actually has changed over the years. Because the techniques that we use to build AI systems and what they can do has profoundly evolved since the early inception of AI in the 1940s to what we do today. All right, so I hope that's better. All right, so I thought I'd start out with just giving a few examples of what AI can do these days. So AI is everywhere. It's hard to really pinpoint a field where AI hasn't made an impact or is about to make an impact. So, for example, in driving, we now have self-driving cars that can do some driving tasks like lane following, overtaking, parking, more or less completely autonomously. That doesn't mean drivers will be completely obsolete anytime soon, but in pretty standard settings on a highway and perhaps in simple scenarios in the city, AI can now drive a car. AI can also help us to get information access. So I'm sure all of you would have used tools like ChatGPT if you want to know something. Instead of searching around and gathering bits and pieces of information, AI can summarize all that information for us and can answer questions. Uh, we can interact with it in natural language. So we don't necessarily need to be an expert in computer programming or in knowledge representation to access information. We can interact in typed language. We can ask a question, type it in, get a response in natural language. We can also communicate via voice. AI has made profound improvements in voice recognition, interpretation of speech, and also to synthesize answers in spoken language, not just written. AI has applications in many fields to support domain experts. For example, here on the bottom left, I've given you an example of medical image processing, where AI might be able to interpret images that radiologists look at to diagnose certain diseases. And so in some fields, like early skin cancer detection, AI can actually outperform humans in the task. In some fields, AI has actually achieved superhuman performance. For example, in games like chess or Go, it's been quite a while since human has won against the state-of-the-art AI player in those games. And so just maybe 15 years ago or so, uh, games like Go were thought to be too hard because we just didn't know how to program the computers to play these games at even basic human level, because the games are essentially quite complicated and there's a large number of possibilities. It's hard to explore them all. But with the advent of AI and machine learning, uh, the computer was able to teach essentially itself on how to play that game, perhaps not exactly in the same way that humans would play, but in a very effective way that can win against most, if not all, human players. And finally, AI has also been used to augment scientific discovery and mathematical sciences. So AI can now effectively use knowledge that's been published in scientific literature and use that to inform the design of experiments that then may lead to, for example, new drug discoveries. AI has made inroads into things like protein structure analysis, where AI helps to fold and analyze the three-dimensional structures of how these proteins are essentially assembled. And that then helps to discover new medicines, get treatments, personalized medicine, and so on. And so these are all very worthwhile examples of what AI can do these days. But what is AI? If I ask all of you, I probably get different answers from all of you. And in fact, there's no I would say there's no single agreed definition of what AI is precisely. In loose terms, you could say, well, AI is to address a task that commonly would require human intelligence to be solved. You might say, okay, driving a car requires human intelligence. Interpreting an image requires human intelligence. Playing a game requires intelligence. But in practice, AI, the term AI has been overused for various reasons. It's used as a marketing hype to some extent, but also in science, the role of or the nature of AI has changed. I think from a very pragmatic view, AI sometimes refers to solving problems that we currently don't quite know how to solve on computers effectively, right? So, and what that entails is different 20 years ago to what it is now. So, for example, in the 90s, doing DNA sequencing and analysis was a hard problem that computers couldn't solve easily. So that was considered AI. Now that problem essentially has been solved. So the AI has been shifted to different problems like language processing, image analysis, and so on. We can also observe that AI is not a single thing. AI actually is a combination of multiple things. And if you look at what kind of traits general AI systems might have, we have perception. We may need to see images, interpret them. We may need to be able to manipulate objects and move around, like in a self-driving car. We may need to perceive what the environment is like, where the road is, where the lanes are, where the other cars are. We may need to issue controls to the actuators of the car to stay on the road, to take a turn, to overtake other cars. In situations like ChatGPT, we might need to interpret natural language. And so natural language is very different to computer code programming languages. They are very precise and narrow. Natural language is very broad and often ambiguous. So it requires that the machine can deal with all that ambiguity and perhaps a variety of structure. AI also needs to be able to learn from experience. So we as humans, we can learn when we do something wrong or we do something right, we learn from that experience so that next time we do the same task or a similar task, we do it better, hopefully. And so AI should have the same capability to learn through experience, to learn from past performances, and to learn from data. If you're looking at, learning is one thing, but if you're looking at playing games, for example, learning from past experience is not necessarily enough. We also need to be able to plan ahead what we might be doing in the next move, what our opponents might be doing. And so this planning ability is also essential to many AI tasks. To solve scientific problems, we also need to have domain knowledge. If we want to solve a problem in biology, we may need some information about how biological things work. What is known about the various concepts and their relationships in biology. And we may need to reason about them to essentially answer questions about that knowledge, answer questions about hypotheticals. What if we do this? What might the effect be? And that then informs the planning and the problem-solving ability of the AI. And so depending on what kind of problem we're solving, each of these traits will have different importance. For example, for a self-driving car, perhaps perception and object manipulation is important. Natural language understanding may be less so. On the other hand, if you're building a system like ChatGPT for question answering, maybe manipulating objects at the moment isn't really important. So depending on what AI system you are trying to build, your emphasis will be on different things. And often, different technologies will be used for some of these traits. For example, knowledge representation and reasoning often requires different algorithms, different solutions than natural language processing. All right, so now let's very briefly look at how the field has evolved from the early inception in the 1940s. If you look at the history of the timeline here, in the 1940s, it was the early days of AI, and most of it was driven by basic things like trying to figure out how to implement basic search methods in computers. The computers at the time were very limited. And so that then led to early systems like the general problem solver who could solve simple things like differentiation of simple formulas, right? And that then led to great enthusiasm because that were problems that previously couldn't be solved by computers. And so there was this big hype saying, oh, we now can solve these simple problems, and in 10 years' time, we're going to be solving all the math problems in the world. And of course, that didn't quite happen. Later on in the 1960s, there were some early natural language processing systems that looked like, how can we make computers interact with humans in natural language? And so ELIZA was a famous example where people could essentially type in some questions or prompts, and the system would respond, simulating a psychotherapist. But that was a really primitive system. It was based on pattern matching. Somebody wrote an algorithm, computer code, and say, if you see these keywords, then respond in this way. And that is great for early prototype, but it's really not enough if you really want to solve some person's problem as a psychologist or a psychotherapist. There was also great expectations in the medical field. So in the late 70s and early 80s, a lot of expert systems were built. And so expert systems, I'm going to show you one of them on the next slide, were basically systems where computer scientists talk to domain experts or doctors, for example, to extract as much of their knowledge in some form of rules and then code these rules in algorithms so that the systems can answer complex medical questions. And so that worked really well in very narrow fields. But as you broaden out the questions, these systems become brittle because, it's simply not possible or very difficult to encode all the knowledge that's required to answer all of these questions. And so the focus of these systems was very narrow and they did not perform well in a broader context. And so that then led to a kind of disillusionment, the first AI winter, where people were saying, AI is all useless. We don't want to invest in AI. We don't want to research in AI. And so that, was not a good time for AI in the late 80s and the early 90s. However, with the advent of better computing hardware, we then had a revival of particularly the data-driven AI, where essentially early statistical methods for machine learning were invented and became feasible, and also advanced algorithms such as IBM's Deep Blue to really play chess, for example, at a better level. And in the late 90s, IBM's Deep Blue defeated the world champion in chess. And so that was a big thing, the first time the computer defeated the world champion in something, in a complex game. In the early 2000s, then there was a bit of a revival of different technologies. So I haven't told you about that. Very early on in the 1940s and 50s, there was an idea of biologically inspired AI, inspired by the brain, where essentially neurons that are individually very simple, if you connect enough of them together, they can solve complex problems. And so that really didn't take off for a long time until the 2000s, where some researchers revisited that idea, and with modern computing hardware, they could build some larger neural networks. And so that then led to quite competitive machine learning systems that could solve interesting problems and compete with the other algorithms, such as regression and classification methods that were in vogue at the time. In particular, in the early 2010s, then these neural network-based systems really took off, in particular in image processing. So in, I think, 2009 or so, if I remember right, there was a paper at one of the computer vision conferences where the neural network basically outperformed all the other algorithms by a large margin. And so that then led to a significant change of the field, where essentially the previous handcrafted algorithmic solutions were replaced by machine learning, deep learning solutions in computer vision. And that has then evolved over the years to broaden out to many other areas as well. In the mid-2015s, generative AI then became the new kid on the block, basically, where AI then could solve not just classification and forecasting problems, but could generate content. In particular, generate natural language content. And so OpenAI's ChatGPT was released shortly after that. And so it's taken off since. And then, of course, now in the 2020s, we have the age of generative AI. There are large language models, generative models everywhere, not just in language, but also in vision, and even to some extent in time series nowadays. And so we can see from the very early search-based and manual crafted solutions, we go to the machine learning-based solutions in the 1990s. We go to the deep learning-based methods in the 2000s to 2010s. And now we are in generative AI. And so for the rest of the talk, I want to do two things. I want to, on the one hand, explain how some of these machine learning methods work. And on the other hand, I want to then demonstrate how the emergence of foundation models in generative AI has changed the way we build AI systems. All right. Oh, yes, this was just an example of one of the medical expert systems that were developed in the 70s. It was called MySyn. It was designed to help doctors answer questions about infectious diseases. And so the system itself, I won't go into detail. The only thing, the reason I'm showing it here is that basically you can see the different building blocks that made up the system. And you can see, okay, there is various programs in there. And these were essentially handcrafted programs. So computer scientists at Stanford sat down, interviewed lots of doctors and say, oh, if you see this, what does it mean to you? What are you going to do next? Which test are you going to run? And then they coded that into rules. And together with some math, the system could then say, okay, if you see this situation, we apply these rules, and then we should do this test or that test, or we conclude that the diagnosis is whatever. And so that works really great for a very narrow field. But as I said before, writing all these programs and acquiring all these rules is a huge bottleneck and a huge effort. So that doesn't really scale to larger problems. So in particular, if you look at real world situations, like image analysis, I think most of you would be hard pressed to come up with an algorithm that can identify what's going on in the scene, how many persons there are, what the specific outline of the person is, what the various objects are, the coins and the music instruments, and then answer questions about that scene. But it's hard enough to come up with an algorithm to identify the outline of the persons in there in a variety of different situations. But then to also answer questions about this, that requires not just detecting what's in the scene, but also interpreting what we see in that scene. All right, we need to know about, for example, that these are musical instruments, that they're used for playing music. People doing this on the street, usually doing that to essentially ask for money. And so that then allows the system to infer what's happening in the scene and also to justify why answer 2 here might be a plausible answer for this situation. And so for any of these situations, how to answer these questions, how to come up with justifications, we don't really know how to do algorithms to do that. But if you show the computer enough examples, the computer can learn to do these tasks with reasonable accuracy. And so that now leads me to how does machine learning work? So in order to train systems or to build systems that learn from examples, we need lots of data. We need a bunch of training data. We need lots of machine learning computer scientists to then use the data to train these models. And so I'll go into how that works in a moment. But basically, training a model involves writing some computer code to set up some kind of structure, a mathematical structure, or bio-inspired structure like a neural network. You apply that structure to the data, you observe what the outcome is, and then if the outcome is not correct, then you adjust the model using some algorithms and rules to make the model better and closer to the correct answer. And so that's typically a training process. So we take the data, we build a model, and then we can apply the model to new data that we haven't seen during training. So we get a new problem like the image I showed on the previous slide. We apply that, the model to this, and we get our answer. And so that's basically how machine learning-based systems work. instead of writing an algorithm on how to solve a particular problem, we compile the training data that essentially shows the system lots and lots of examples of this problem that we want to solve, and then hope that during the training, the system will learn relevant patterns in the data to then solve problems that we haven't seen. And so, of course, the different models that we can use and the different algorithms that we can use to train these models from the data, there are many, many of those. I can't possibly go into all of them. Even how to measure the difference between the expected outcome from the training examples and what the model produces and how to use that for training. Again, there are lots of technical solutions in there that are beyond what I can present here today. Instead, I want to focus on three fundamentally different ways of machine learning. So we can look at the different ways to train models and group them into three different categories: unsupervised, supervised, and reinforcement learning. So unsupervised and supervised basically differ by what data we have available. So in unsupervised learning, we only have the data, but we don't know what the answers are. Okay, and so that's, for example, if you look at the example in the supermarket, you buy something, and the supermarkets want to know what items are bought together commonly. Right? So we only know what people have bought, but we don't know what the patterns are that we want to find. And so then we apply unsupervised machine learning, and the algorithms there will tell us maybe people buy milk and bread and nappies together very frequently or something like this. And then a business analyst can use that to set pricing and do whatever. Right? So in unsupervised learning, we only have the data, but we don't know the answers. In supervised learning, on the other hand, we have the data plus the answers that we expect the system to produce. So for example, if I show you an image of a cat, then we might ask the system, okay, what animal is in this image? And we expect that the system will say cat. And so our training data now has more information. It doesn't just have the images, it also has the labels or the outcome that we expect. Right? And so that makes it a little bit harder to apply this kind of techniques, because we now have to have this labeled data. We have to somehow generate all the correct answers for all of the samples in our training data. And finally, we have reinforcement learning. So reinforcement learning is learning from feedback. If you imagine maybe a robot and you want the robot to learn how to walk, then the robot actually, it's really hard to come up with a supervised scenario to tell the robot, oh, now you have to gonna move the joint by that many degrees. That we don't really know how to do that. So instead, what we can try is we can just let the robot loose in an environment and say, okay, now you learn to walk. And initially the robot might move around randomly and not know what to do, but the robot will get feedback and say, hey, you've just moved 2 steps. That was really great. Keep going. And so from this feedback, the AI can then learn which actions are successful in certain situations to reach a certain goal and which actions are perhaps not useful or detrimental. And so if you do this lots and lots of times, then reinforcement learning can learn what's called a policy on essentially what to do in what situation. Right? And so it turns out that in most contemporary machine learning systems, we use combinations of all three of these learning techniques to build our model. Right. Yeah, so just another example of supervised learning. So we've got our labeled data, we have the images, and each one is labeled with cat or dog, and we feed that into our model training. And then in the end, we might get a model that tells us for each image, is it a cat or a dog, right? And that's really good. So if you look at, for example, image classification, object detection methods, then this can be a way of training that model. Right? If you look at a self-driving car, we might need to pick up where the other cars are. And so there might be a model in there that essentially is trained to detect other cars, to detect pedestrians, to detect the lane. And so that might be trained in this way. Yeah, unsupervised learning is just about identifying the patterns in the data, maybe groups of similar things, patterns of stuff being brought together. And so that can be useful, but sometimes unsupervised learning models are also used to detect anomalies and say, okay, are there any examples that don't fit any of the patterns that we've learned? And so that can also be useful for applications. Yeah, common applications of unsupervised learning include market basket analysis that I said before, but also things like social media analytics. If you say, okay, if you want to analyze the structure of your friendship relationships in social media, then there also are unsupervised methods that try to predict who might be friends with whom, and what are the patterns that determine whether certain information might propagate in social networks. All right, reinforcement learning, yeah, so it's learning from feedback. We have our agent. An agent takes an action. Let's say playing a computer game, we might steer our avatar around, or our Pac-Man in this case. And depending on what we're doing, we might win some points or we might lose the game. And so we get a reward and we get an observation. So the reward tells us how well we are doing based on the game, for example, the simulation of Pac-Man. And the observation tells us what is the resulting state of the game if you move Pac-Man, for example, to the right. Right? And so in environments where we can do this lots of times without essentially destroying our robot, that's a really effective way to learn how to play games, for example. Right? And if you want to know what this might look like after we train the model, there's a little bit of a video there. Oops. If this works, we can see how the AI basically has learned through this process how to play the various games. And so to learn how to play games, the model received a screenshot of the game, perhaps a previous screenshot, and the score that it achieved at each step. And so based on that, it then learned how to essentially play the game. And so for some games like Pac-Man, Breakout, and so on, the system actually performs better than humans. For some other games, the system isn't quite as effective yet. All right. So now we've looked at the different types of machine learning. So next, I'd like to look at some of the machine learning techniques that are now prevalent in large language models. And they are neural networks. And so neural networks are a biologically inspired paradigm for computing. And so if you're familiar with our brain works in a very simplified way, we have essentially our nuclei in the brain. They have dendrites through which these cells receive signals from other cells, and then they process that in some way, and then they emit signals via the axon to feed that signal to other cells. And so, of course, the biologists will probably tell me I'm all wrong, but that's part enough that we need to know about how the brain might work to understand how neural networks work. And so neural networks are essentially a mathematical simplification of this process. We have our nodes that are connected to other nodes, and so nodes receive inputs from previous nodes via the connections. They aggregate that information somehow, and then they output new information that then is received by the neurons in the next layer. So that's essentially in a nutshell how a neural network works. We feed some inputs in there. So each of these nodes might have a value, 0, 1, or maybe some other value. Mathematical functions in there process these values to compute the output, which is then received by the next layer, and that process repeats. All right, so it's really simple building blocks, but put together, we can do interesting things. And so early on, a neural network would have maybe 2, maximum 3 layers, maybe a handful of neurons. And so these things couldn't really do much. They could approximate certain functions, maybe solve simple classification problems. But to solve interesting problems like the image analysis problem I showed you earlier, we need neurons, or we need neural networks that are bigger than this. All right. And so with the advent of computing power in the early 2000s, we could then finally build bigger neural networks that could solve more interesting problems. And so that led to the field of deep neural networks. So early on, deep might have been 2 layers. The deep neural networks these days have up to 100, if not more, layers in them. All right. And they can have billions or trillions of connections. So if you look at a model like GPT-4, it's not exactly known how many connections it has, but we estimate it has about 1 trillion connections. Compared to the human brain has about 100 or 1,000 times more connections than that. So there's still some way to go, but these models are really humongous, and they're starting to become really reasonably close to the number of connections in the human brain. That doesn't mean that soon GPT-4 is going to be smarter than us, because the actual biological neurons have much better capabilities of information processing than these individual mathematical nodes. So we can't really compare them one by one. But nevertheless, these big networks are now sophisticated enough, they are large enough to approximate not just simple functions, but to solve interesting problems. Like if you've used any form of generative AI, ChatGPT, Gemini, or anything, they can solve reasonable questions, right? They can be sometimes smarter than I am. And so what can we do with those deep neural networks? So the early success of these networks really was in computer vision. If we look at image analysis, object detection, object segmentation, so this is where these models shine. And so there are different types of neural networks. There are convolutional networks. There are fully connected neural networks. There are essentially recurrent neural networks that are designed to do time series. But at first, it was really the convolutional networks that shone on those image analysis tasks. All right. And so now let's see what happened later. So with the convolutional networks and the image analysis, they were usually trained using some form of supervised method. Annotators were annotating images to highlight all the cars, and then that was used to train these models. And so that works fine for some problems, but it's really laborious and expensive. So then the question is, can we simplify this process somehow? What do we do for natural language? It's not in natural language, the problem is much more complicated because language is richer, it's more diverse, it has more intricate structure than an image. And so labeling there then becomes much more complicated. For example, if I ask you to explain what machine learning is, each one of you will likely give me a slightly different answer. And so what does that mean for machine learning? You know, I can't just use supervised learning easily to train these models. So the idea that came about then was to actually use some form of unsupervised learning, where we can try to train these models without having the labels. So the idea was that we can actually use the same text that we use for input as the labels for the output to train the model. And in particular, the key idea here is that we're going to mask out some part of the input. We omit some words. And we're going to ask the model, given the other words in the text, predict what that missing word is. And so we can easily do that. We got all the text, right? If you open a book or a website, you have the text there. And that's all you need to do this training. You mask out some words, you train the model to predict the missing word. And it turns out that is already enough to build a pre-trained model, language model, that we can then use as the basis for other tasks. For example, what we might do is we might pre-train a model like this, and we might feed the text in and put some neural network on top of this to then decide on, okay, based on what the model spits out, is the text maybe a positive phrase text or a negative phrase text, or what kind of sentiment it might have. And so that way we can use these pre-trained models to more easily solve interesting tasks, because now the situation has changed slightly. We can use all the text in the world to pre-train this thing, to make it as good as possible language model. And then we put a small layer on top of this to then solve the specific task that we're actually interested in. And so in that way, we can use all the patterns and all the knowledge that this model has learned about the text to inform how we decide, for example, sentiment analysis in the text. And so that's really a very simplified way of saying how these models are trained. And so what else can we do from this? Well, we can then use these models to train them further to what we call using instruction tuning. And so we take a basic pre-trained language model and we essentially train that model further to not just predict what the words are, but we also train it to solve certain tasks. All right. And so then if we do that long enough and well enough, we might get something like a chatbot, like ChatGPT. We can ask it a question and it will give us an answer. And the interesting thing with this is if you have a language model that is large enough and it has been trained on instruction following well enough, then this thing can actually answer questions that it hasn't seen before during training, right? So no one might have asked the model how to explain what a language model is to a 5-year-old, but anyway, it comes up with some answer. Whether that answer is completely accurate is a different story, but at least it comes up with something that that looks reasonable. Right. All right, so that was essentially how we arrive at ChatGPT-like systems. But we can go even further than that. Who says that we are limited to text only? We can use images and text together, and even videos and audio and all sorts of other things that we might have available, so that the model can learn jointly from all of those data sources. Right? For example, we can take an image and we can take a label of that image that we might have found somewhere, and then we can feed that into a model. And so the model will learn a relationship between the image and the text. And so that we can then solve problems that involve multiple modalities. For example, if you wanted to caption, for example, an image and say what's in that image, we can then use the resulting model to show it the image, and the model might spit out the caption. Or we can go the other way around. We might describe an image, and the model might spit out an image that matches the description, hopefully. I mean, the process that sits under these kind of generative systems is more complicated than this, but in a nutshell, that's what it is. The model learns some kind of joint relationship between the different modalities and then uses that to enable it to solve interesting problems that involve multiple modalities. Here, example of DALL-E, we can put in a description of what we want, and then it will, the AI generator will basically generate a number of images that hope more or less match that description. And so that works not just for images, but these days you can do this for videos. Obviously, you can do it for audio. If you want to clone someone's voice, for example, that is now reasonably easily possible. All right, so we now have these pre-trained models that have been trained on essentially any data that we can find on the internet and who knows where else. And now, so how do we use that? So it turns out that the way we use and build AI systems has changed profoundly from the early 2000s to now. So in the early 2000s, it was basically a feature-centric approach where some machine learning and computer science experts sat together to essentially figure out what are interesting features that we can compute from the data, and then build models specifically to solve one task. For example, in the image classification example, people might have looked at various features of the images and distribution of pixels and trying to identify regions that share the same colors and stuff like that, and then use that to inform classification tasks. So with the advent of deep learning, that changed somehow. We now have the ability to pre-train models on all sorts of data and images, and then use that pre-trained model, put a smaller layer on top, and then train essentially only that smaller layer to take the output of the pre-trained model and then turn that into a solution for the actual task we want to solve. And so the advantage of doing that is that we now need less expertise on extracting all the features, and we may need less data because this thing is much smaller than the complete pre-trained model. And that means in terms of machine learning, we need less data to reliably train that classification system, for example. All right. And so that now with the advent of generative AI, we can go even further. We have these generative models that have been tuned to solve not just one problem, but solve a variety of problems. And so we can now use them as a starting point, and we can instruct these models to solve different tasks. Right? So that then means we may need no or very little data to actually use an AI system to solve a specific task that we're interested in. And so that now essentially has led to a new paradigm where we use pre-trained models, foundation models, instruction-tuned models to solve a variety of different tasks using that pre-trained model as the basis, and then do relatively little adaptation to solve each of these specific problems. And again, that has implications on the level of expertise that is needed and the amount of data that is needed to solve each of these tasks. And so how do we, so I've explained a little bit of how this pre-training works. And so now what mechanisms do we have to actually use a pre-trained model and adapt it? And perhaps the most prevalent method at the moment is what's called in-context learning. And so in-context learning basically uses a pre-trained model, and as part of a prompt, as part of the instructions we give to the model, we also give some examples of the task we want to solve. And so usually these are not very many examples, sometimes a handful, sometimes a few tens or hundreds. And so then we expect that this pre-trained model will be able to identify patterns in these examples, mesh these patterns together with what it has already learned during the pre-training to solve the task that we want to solve. All right. And so that's what we pretty much do every day if you use ChatGPT or Gemini. We instruct the model to do something. We might show it a few examples of what we might want to do, perhaps a few examples of input and output that we expect. And then we tell to the model, okay, here's a new thing. We want to know what the translation of cheese is, and expect that the model will come up with the correct answer. But again, that's great for us because we need very little expertise in terms of machine learning and training and so on to do that. All we need is a bunch of examples and a little bit of skill to find the right prompt to instruct the model correctly. So that's great if we can easily provide these examples. But what if we are working in maybe the medical field where we might not immediately be able to supply all the relevant knowledge that we might need to solve the question that we have? And so then that led to the idea of combining a pre-trained model with some kind of database, information retrieval. We have a database that has all sorts of documents, maybe everything that was published in the medical literature or in various medical guidelines. We have all that in the database stored and indexed. And now we get a question. We can use a pre-trained model to try and find what are all the relevant documents that are in this database that might relate to this question, and we retrieve all of them. We add that to the question that we have and feed that into a pre-trained model. And say, okay, here now is our question. And here's all the bits of information that we found that might relate to this question. Give me an answer. All right. And so that's a very common way these days to inject additional knowledge into the language model. For example, we can't expect that ChatGPT or Gemini might be experts in the medical domain in all fields, or they might not be experts in whatever we are doing. If you're doing predictive maintenance, perhaps ChatGPT was not optimized to do predictive maintenance decisions. But we can add the relevant information through this type of process to augment that initial instruction, to augment the prompt, and then solve domain-specific problems without actually having to go through a detailed training and tuning process of that model. And so this is about the simplest RAG model that exists today, but you can, of course, make this step more sophisticated by looking at things like graphs, for example, to see what might be related concepts and explore that graph of documents and concepts and information to augment your question. All right. Yeah, so there are other ways that we can tune these models, but I might skip over that just to say that there's also a reinforcement-based way to tune these models, where you generate multiple answers and somebody will give feedback and say, oh, I like this answer better than that answer. And then the model can learn from that to next time give a better answer as well. And so that's particularly useful if there's humans in the loop, because humans are really bad to say, this answer is a score of 3 and this one is a score of 5. But to say, this one is worse than that one, we are really good at that, at least better than giving absolute scores. And so last but not least, the latest evolution of all these processes now to hook up language models and pre-trained models to two things: to memory that basically gives the model some ability to remember what we've asked it before, so it doesn't forget about the previous questions we had, and tools or other agents, where basically the LLM gets access to things like doing a web search, looking at something up in a database, invoking some domain-specific tool to compute something. And so the process here is that we get a question into the LLM. The language model will decide on what action it should take next, whether it should directly generate an answer, whether it should access its memory, whether it should invoke some external tool to get more information. And then this process repeats until it decides, okay, now I got enough information to actually spit out an answer. And so this is called LLM agents or agentive AI systems. And so that's basically the principle that the LLM drives that process of decomposing the complex question into individual bits that it can solve either directly, it can look it up, or it can invoke other systems that might provide part of the answers to this question. All right, so that's where we're at. And so the idea here is that some of these tools might already exist, or some of these tools might be other pre-trained models that we've optimized to solve certain subtasks that we might want to solve. Yeah, again, I won't go into details, but this, of course, this can then be put on steroids, where you have another language model giving feedback to the language model, so that essentially one language model can teach another one to solve a task better. Again, yeah, lots of different ongoing work in that area. All right, that brings me to the end of today. So hopefully I gave you a little bit of an idea of how AI has evolved throughout the years. That AI involves lots of different things. It's not just algorithms, but it also requires that we need to think about what the different traits are that we want to solve, the perception, the reasoning, the actuation, and the learning. And so most of the current AI technologies are based on some form of deep learning. And so deep learning powered breakthroughs in computer vision, but also in speech processing and other fields. And so deep learning is really a very simple conceptually approach, but it's very hard to make it work in practice if you have very deep networks with lots of neurons. So you need lots of expertise to really train these models to perform well. And so that expertise is scarce and requires huge resources. So the reason that you don't have thousands of different large foundation models these days is that it costs millions of dollars to train one of them. And you need the right team and experts to do it. So that's why the effort of building these models is now concentrated with some of the large corporations around the world. But the models they produce can be applied with relatively little knowledge and little expertise. So foundation models have really changed the way we build applied AI systems. We use the pre-trained foundation models, we tune them, we augment them using techniques like RAG to quickly come up with solutions for domain-specific problems. Having said that, not all problems are well suited to AI. Just because you have a large language model that can multiply two numbers together doesn't mean you should be doing all multiplying with large language models. So think carefully about whether AI is really the right solution to your problem. And in particular, you hear about AR and XR. AI can be part of it, can be part of the solution, but it must be designed and considered as part of a human and AI system. But when you design an AI system, you need to think carefully how it's going to be used, how people will receive it, how it will really augment what the humans do, and where it is that the AI can shine and where it is that the humans can shine. And so, yeah, hopefully you get some opportunity to explore that a bit more in the rest of this short course. So thanks for having me. I hope I haven't confused you more than I could answer. But yeah, if you have any questions, happy to take questions.
Like I mentioned before, I'll be sharing the recording video for you later as well. So does anybody have any questions? And also I'll check online to see. We've got about 25 people online. Any question? I think there's a really clear explanation, especially the various phases that AI has gone through. So that was a really nice explanation of categorizing that. Anybody in the room have any questions here?
No, I just want to say thank you for someone with no tech background that really broke it down and made it really simple. So I really appreciate that. Thank you.
Yeah, thanks. I hope I succeeded a little bit. Yeah, sometimes it's hard for me to abstract from all the technical bits and pieces.
Right.